So we looked at Euler paths, and remember an Euler path is a path that visits every edge exactly at one time. You're not allowed to revisit edges. So we need to find something called a Hamilton path. Something a little more complicated than an Euler path as far as determining these things. So what's a Hamilton path? A Hamilton path in a graph G as a simple path. So a simple path just means you're not allowed to double cross edges. You can't use an edge more than once. Is a simple path passing through every vertex exactly once. Passing. Not every edge exactly once. Every vertex passing through each vertex. That's the key here. Each vertex. Exactly once. So you have to hit every vertex exactly one time. Not every edge, but every vertex. You're just not allowed to use up edges more than one time. What about a Hamilton circuit? A Hamilton circuit so we're defining. In a graph, G, it's a simple circuit, is a simple circuit. So that's a circuit that doesn't double cross any edges. So every time you cross an edge, you're not allowed to go back over that edge. And a circuit means you beginning and end at the same place. It's a simple circuit. Passing through every vertex exactly once. Passing through every vertex exactly once. So basically a Hamilton circuit is a Hamilton path that begins and ends in the same position, the same vertex. All right, so here's an example here. So determining whether or not something has a Hamilton path is not so easy. But if there's one, you can just find it. So we're not going to get too hung up on showing why there is one. Let's see, find a Hamilton path. So I'm telling you there is a Hamilton path in this graph. So let's actually find a Hamilton path in the graph. Okay, number one. So here we're going to have A, B, C, D, E, F, G, H, B, C, D, E, F, G, H. So here we go. That's what our graph's going to look like. And there should be a diagonal here. Okay, let me get rid of this E. The E is kind of in the way. Let me move it up here. Well, there we go. So I want us to find a Hamilton path. A Hamilton path. So it doesn't have to begin and end at the same place, right? It's not a circuit, it's just a path. So we're going to try to start somewhere, and we're going to try to hit every single vertex. So I'm going to start at H here. You don't have to use up every edge. Don't use up every edge. I'm going to go from H to A, from A to B, from B to C, from C to D. I just have to make sure I hit every vertex. C to D, there are a couple of ways we can go. We can go D to G. We can go G to E and E to F. This is a Hamilton path, right? It's a simple path. That means a path that we didn't double cross any edges. We used every edge here, at most one time. So we didn't double use edges, we didn't repeat edges, and we hit every vertex. We don't have to hit every single edge though. All right, so number 2, give another Hamilton path. All right, here is, no. This one is a Hamilton circuit. Examples. Find a Hamilton circuit. So this is going to be a Hamilton path that begins and ends in the same place, right? A circuit has to begin and end at the same place. This will be 2, I'll call it. All right, so we're going to have here A, B, C, D, E, F, G, H, B, C, D, E, F, G, H. All right, so A to B, B to C, C to D, D goes back to A connects to F, F connects to G, G connects to H, H connects to E, E connects to F, B connects to G, C connects to H, E connects to D. All right, that's our graph. So we want to find a Hamilton circuit. We got to begin and end in the same place. That's the idea. I'm going to start here at A. Let's see if I can get this. A goes to, let's say, B. Where can we go now? I'll go from B to G. I got to hit every vertex. Every vertex exactly at once. And I can't double back on any edges. H can go to, so G can go to H. H can go to C. C can go to D. D can go to E. E can go to F. And F can go back to A. Not writing. There we go. Yep, so there it is. There is a Hamilton circuit, right? We began at A and we returned at A. We hit every vertex. Didn't have every edge. It's okay, you don't have to hit every edge. All right, let's do another one. This one's asking for a Hamilton circuit as well. All right, what do I got? All right, we're going to call this A, B, C, D, E, F, G, H, I. All right, so there apparently is a Hamilton circuit here, we're told. So let's see, where am I going to start? I'm going to try starting at A. I don't know if that's a good place or not. We'll try it. I'll try, I don't know. Is that a good place or not? I'm going to try A to H. This may not work. We'll see. Then H to B. Sometimes it's tricky doing these. Then B to C. Got to hit every vertex. Then C to D. Then D to I. That's not going to work. That's not going to work. Okay, I can see already that's not going to work. Because we're going to have to come back and we're not allowed to hit that vertex again. So let's go back. All right. No, the wrong color. I can see there was a problem there. All right, let's go from D to E. This will work. And then E to F. Then F to I. Then I to G. And then G to A. There we are. That is a Hamilton circuit. A Hamilton circuit. Visits every vertex exactly once. So, there really is not a necessary and sufficient condition for a Hamilton circuit like there was with the Euler circuit. Euler circuits are nice. All you have to say is, oh, it's a connected graph with all even degree vertices, so therefore we're dealing with an Euler circuit in this graph. But there's no such if and only if statement for a Hamilton circuit. Hamilton circuits do not have necessary and sufficient conditions. No necessary sufficient conditions that are both. But there are some strategies for determining whether some things may or may not be Hamilton circuits. We're going to look at some of the strategies for why there may not be a Hamilton circuit. So some useful facts. These are facts about Hamilton circuits. Facts about Hamilton circuits. These will be useful for determining if they're not Hamilton circuits within your graph. Fact 1. If a graph G has a vertex of degree 1, then G has no Hamilton circuit, then G has no Hamilton circuit. Let's think about that. So imagine here you have a graph with some stuff over here, blah, blah, blah. Blah, 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 right? Blah, blah, blah. This is all blah, 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 blah over here. And here you got A, and here you got B, okay? And let's say A has degree 1, right? A has degree 1. It has just one edge coming out of it. So if you go out of A, there's no way to get back to A, right? There's no way to get back to A. If you try to get back to A, you're going to have to double cross the edge AB. So you won't have a Hamilton circuit, right? So if you're going out of A, you have to go to AB. You're going to have to come back through to get back through to A, right? You want to end back up at A, you're going to have to go back across BA, which that'll use that edge more than once. You're not allowed to use edges more than once in a Hamilton circuit. You have to hit every vertex exactly once, but you're not allowed to double use edges. So if you have a degree of 1, if you have a vertex of degree 1, then you will not have a Hamilton circuit. That's an important fact. Here's another fact. If a graph G has a vertex of degree 2, then both edges emanating from that vertex must be a part of the Hamilton circuit. Then both edges, I should say, both edges. Emanating from the vertex. Must be a part of the Hamilton circuit, must be part of the Hamilton circuit. Let's think about that. So let's say you have a vertex, right? Let's just call it x. And it's degree 2, right? If it's degree 2, then it has what? 2 edges. 2 edges going to x, right? If that's your vertex. So remember that every Euler circuit has to hit your vertex x, right? Has to hit your vertex x. So your Euler circuit has to hit the vertex x. So you're going to have to go through that first edge and come out of that second edge. So you're going to use up both of those edges. That's the idea. Now, fact 3. Here's another useful fact. Fact 3. If a graph G has a Hamilton circuit, then it cannot have a smaller subcircuit then. It cannot have a smaller subcircuit within it. Yeah. So the idea behind this is, okay, so let's say you got something that has a Hamilton circuit, right? I'll just do a little example here. I call this what? A, B, C, D, E. So your Hamilton circuit is in your graph. So, I mean, you got some graph out there, and this is going to be the Hamilton circuit within it. A, B. It goes through these vertices. So if for some reason, this is your Hamilton circuit, and then you have some subcircuit in here. Let's pretend you had a subcircuit. You'd have to create a subcircuit in there. Well, that's impossible, because if this is your Hamilton circuit now, the blue combined with the red, then you're going to be visiting some of these vertices more than once, right? You're going to be visiting the B vertex more than once. You're going to be visiting the E vertex more than once. So it's impossible to have any such smaller subcircuit inside of a Hamilton circuit. So you have to get rid of it. Can't happen. Okay, so useful facts. So these will probably be the useful facts that we'll use, these 3 useful facts, for showing that something doesn't have a Hamilton circuit. These will be the 3 big ones. So number 1, if you have a vertex of degree 1, you will not have a Hamilton circuit. That's a really easy one. And then number 2 and number 3 we're going to use together, usually in conjunction. They often go together in conjunction, not always. Sometimes 3 you can use on its own, but 2 a lot of times goes with 3. So remember, with 2, fact 2, if you have a vertex of degree 2, then both of the edges that connect to that vertex of degree 2 must be a part of your Hamilton circuit. In fact 3, you can't have any subcircuits. If you have a subcircuit within your proposed Hamilton circuit, it really isn't a Hamilton circuit.